Okay, hi everyone. So, last time we discussed various memory management strategies, and these strategies have the same goal, which is to keep many processes in memory simultaneously that can allow multi-programming. However, we have noticed that it is a requirement that the entire process should be in a memory before it can execute. So, a method to solve this is by using virtual memory. And virtual memory is a technique that allows the execution of processes that are not completely in memory. And one major advantage of this scheme is that programs can be larger than physical memory. However, we will discuss that virtual memory is not easy to implement, and it can decrease the performance of our computer systems if it is used carelessly. So in this particular chapter, we will provide a detailed overview of the virtual memory, and we'll try to examine how it is implemented and explore its complexity and benefits. So the outline of our discussion will be the following. We will discuss the background, demand paging, copy on write, page replacement, allocation of frames, thrashing, memory map files, allocating kernel memory, other considerations, and some operating system examples. The objectives of the topic: at the end of this topic, you should be able to define virtual memory and describe its benefits, illustrate how pages are loaded into memory using demand paging, apply the first in first out, optimal, and LRU page replacement algorithms. And we'll try to describe the working set of a process and explain how it is related to program locality. And then we'll describe how Linux, Windows 10, and Solaris manage virtual memory. And we'll try to design a virtual memory manager simulation in the C programming language. So for the background, as we have repeatedly said, uh, every code that needs to be executed should be in the physical memory. But the problem is sometimes the entire program is rarely used even if it is inside the memory. So the first approach in meeting this requirement is to place the entire logical address in the physical memory, and we use dynamic linking for these restrictions. But the problem with dynamic linking, it generally requires special precautions and extra work by the programmer. In some examinations, it has been seen that some of the programs, for example, in some real programs, it shows us that in many cases, the entire program is not needed. For instance, for some cases, for example, some of the programs has error codes. No? Sometimes they have code to handle unusual error conditions, unusual routines, and these errors occur in practice, and this code is almost never executed, for example. And some have a large occupies large amount of space in the memory. Like for example, when arrays, lists, and tables are loaded in the program. So for example, an array may be declared 100 by 100 elements. So even though it is seldom larger by 10 by 10 elements. So basically those things are the things that we usually seen as the problems regarding the allocation of the memory. So some programs, they no longer constrained by limits of physical memory, and sometimes each program takes less memory while running, while some programs or more programs run at the same time. So basically, the If we run all those programs that, for example, not entirely in the memory, it would probably benefit both the system and the users. And that's where the virtual memory comes. Now, virtual memory involves the separation of logical memory as perceived by developers from the physical memory. And this separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. So what the virtual memory makes is the task of programming. It makes it more easier because the programmer no longer needs to worry about the amount of physical memory available. So they can concentrate instead on programming the problem that is to be solved. Now we have what we call a virtual address space, no? And the virtual address space of a process refers to the logical or virtual view of how a process is stored in the memory. And usually it starts at address 0, for example, and then it exists in a contiguous memory, so until the end of the space. Meanwhile, as we have learned, physical memory are organized in page frames, and the one that maps the logical address to the physical memory is what we call the memory management unit. Now, the virtual memory can be implemented via two ways. They can be implemented using demand paging and demand segmentation. So here is an illustration of the virtual address space. So in this illustration, we can see that the design of the logical address space for the stack to start at max logical address and grow down while heap grows up. So this means that we allow the heap to grow upward in memory as it is used for dynamic memory allocation. And similarly, we allow for the stack to grow downward in memory through successive function calls. So this large blank space or hole between the heap and the stack is part of what we call the virtual address space, and it will require actual physical pages only if the heap or stack grows. So this virtual address space that include the holes are known as the sparse address spaces. This allows for the growth and dynamically linked libraries, etc. So in this illustration, we can see a shared library using the virtual memory. The system library, such as, for example, we have given an example of a shared library such as the standard C library, which can be shared by many processes through mapping of the shared object. It is being shared by shared object such as the shared library here and the other shared library here. So it creates a virtual address space which is called now the shared pages. And although each process considers the libraries to be part of its virtual address space, the actual pages where the libraries reside in the physical memory are shared by all the processes, now, as you can see from this illustration. So typically, a library is mapped read-only in the space of each process that is linked with it. Now, we have seen some problems about loading programs into the memory, and we have seen that sometimes we could bring an entire process into the memory at load time, or sometimes we can bring a page into a memory only when it is needed. So this option of bringing a page into a memory only when it is needed is what we call demand paging. So this is what demand paging is all about. So this is an alternative strategy to load the pages only as they are needed, and this technique is what we call the demand paging, and now commonly used in virtual memory systems. So with the demand page virtual memory, the pages are loaded only when they are demanded, alright, during program execution. So pages that are never accessed are never loaded into the physical memory. A demand paging system is similar to a paging system with swapping, where processes reside in secondary memory. So the concept of demand paging is that, as we have mentioned, it is used to load a page in the memory only when it is needed. And as a result, for example, while the process is executing, some pages will be in this memory, in the main memory, and some will be in the secondary storage. So we need some form of hardware support to distinguish between the two. So what we have is the valid and the invalid bit scheme, which was described in the previous lesson and which can be used for this purpose. So we have learned about the page table with valid and invalid bit. So what happens if the bit has been set to valid? So that means the associated page is both legal and in the memory. But if the bit is set to invalid, then the page either is not valid, not in the logical address space of the process, or is valid but is currently in the secondary page or secondary storage. So this page table entry for a page that is brought into the memory is set as usual, but the page table entry for a page that is not currently in memory is simply marked invalid. So this is the situation. But what happens if the process tries to access a page that was not brought into the memory? Though the access to a page marked invalid causes what we call the page fault, no? Wherein the paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. And this trap is result of the operating system's failure to bring the desired page into the memory. So the procedure for handling this page fault is straightforward. So the first procedure for handling this page fault is to check an internal table. So usually it is kept with the process control block for this process to determine whether the reference was a valid or an invalid memory access. So if there is a reference to a page, first reference to that page will trap to the operating system, and that is going to be the page fault. Now, if the reference was invalid, we terminate the process. Okay, so it's being aborted. But if it was valid, but we have not yet brought in that page, we now page it in. So we just go to the step 3. And what is step 3? We find a free frame by taking one from a free frame list, for example. Right? So that is going to be the number 3. I think there is an illustration here. This is the illustration. Okay. So number 1, again, we check an internal table. We check from the table for the process to determine whether the reference was valid or invalid. If the number 2, if it is valid, we have to page it if it is valid. But if it is invalid, we terminate the process. Number 3, we find a free frame by taking one from the free frame list. Okay? And in number 4, we can see we can schedule a secondary storage operation to read the desired page into the newly allocated frame. That means we have to bring in the missing page. Okay? And from number 5, when the storage read is complete, we modify the internal table kept with the process, that is to reset the page table and the page table to indicate that the page is now in the memory. Lastly, number 6, we restart the instruction that was interrupted by the trap. So the process can now access the page as though it had always been in the memory. Now, in the extreme case, we can start executing a process with no pages in the memory. So when the operating system sets the instruction pointer to the first instruction of the process, which is on a non-memory resident page, the process immediately faults for the page, or we call it page fault. Now, after this page is brought into the memory, the process continues to execute, faulting as necessary until every page that it needs is in the memory. At that point, it can execute with no more faults. And this scheme is what we call demand paging, or pure demand paging, wherein it means never bring a page into memory until it is required. So theoretically, some programs could access several new pages of the memory with each instruction execution, possibly causing multiple page faults per instruction. And this situation would result in unacceptable system performance. Fortunately, analysis of running processes shows that this behavior is exceedingly unlikely, and programs tend to have locality of reference. So the hardware to support demand paging is the same as the hardware for paging and swapping. So we have the following hardware support needed for the demand paging. We have the page table. What is that page table? This table has the ability to mark an entry, whether it is invalid or valid, through a valid-invalid bit or a special value of protection bits. Second, we have the hardware support needed. We have the what we call the secondary memory, and this memory holds those pages that are not present in the main memory. So the secondary memory is usually a high-speed disk or a non-volatile memory device. So it is known as the swap device, right? So this is known as the swaps device, and the section of the storage used for this purpose is known as the swap space. So the swap space allocation will be discussed later. Okay? And lastly, we have what we call an instruction restart. So basically, what is this? This is the most crucial requirement for demand paging, which is the ability to restart any instruction after a page fault. Now, when a page fault occurs, the operating system must bring the desired page from the secondary storage into the main memory. And to resolve the page faults, most operating systems maintain a free frame list, which is a pool of free frames for satisfying requests. And these requests are what we call the free frames must also be allocated when the stack or heap segments from a process expand. So the operating systems typically allocate free frames using a technique known as zero fill on demand, which means the content of the frame zeroed out before being allocated. Alright? So zero filling on demand frames out are zeroed out before being allocated means they are trying to erase their previous contents. Now when a system starts up, all the available memory is placed on the free frame list, and as the free frames are requested, the size of the free frame list shrinks, and at some point the list either falls to 0 or falls below a certain threshold, at which point it must be repopulated. Now let's try to discuss the performance of the demand paging. Demand paging can significantly affect the performance of a computer system. To see why, we can try to compute the effective access time, or the EAT, for a demand page memory. Assume that the memory access time denoted, for example, MA, is 10 nanoseconds, and as long as we have no page faults, the effective access time is equal to the memory access time. But if there is, however, a page fault occurs, we must first read the relevant page from secondary storage and then access the desired word. So what does this mean? So we can assume the probability of the page fault, so we can compute the effective access time as 1 minus the probability multiplied by the memory access time plus the probability multiplied by the page fault time. So to compute the effective access time, we must know how much time is needed to service a page fault. And a page fault causes the following sequence to happen. So if there is a page fault occur, the following sequence is going to happen. This is what we call the worst case, the stages in the demand paging. First, there will be a trap to the operating system. Second, save the user registers and process states. And then third, determine that the interrupt was a page fault. Fourth, check the page reference was legal and determine the location of the page on the disk. Fifth, issue a read from the disk to a free frame. Letter A, we can wait in a queue for this device until the read request is serviced. B, wait for the device seek and or latency time. And C, begin the transfer of the page to a free frame. So continuing, number 6, while waiting, we can allocate the CPU to some other user. 7, receive an interrupt from the disk input-output subsystem when the input-output is completed. Number 8, save the registers and process state for the other user. 9, determine that the interrupt was from the disk. 10, correct the page table and other tables to show the page is now in memory. 11, wait for the CPU to be allocated to this process again. And lastly, number 12, restore the user registers, process state, and new page table, and then resume the interrupted instruction. So we can note that not all of these steps are necessary in every case, no? For example, we can assume that in step 6, the CPU is allocated to another process while the input-output occurs. So this arrangement allows multi-programming to maintain CPU utilization but requires additional time to resume the page fault service routine when the input-output transfer is complete. So in any case, there are 3 major task components of the page fault service time. So this task components of the page fault services time are the following. We have the service the page fault interrupt and read in the page, and lastly restart the process. So the first and the third task can be reduced. No? Service and interrupt means careful coding means just several hundred instruction needed, and restart the process. That means to just small amount of time is to do again the process by restarting it. Okay. Now the first and the task, as I have said, can be reduced with careful coding to several hundred instructions. but these tasks may take from 1 to 100 microseconds each. Alright? So we can take, for example, the case of the hard disk drive being used as the paging device. So the page switch time will probably be close to 8 milliseconds. So because the typical hard disk has an average latency of 3 milliseconds, and a seek of 5 milliseconds, and a transfer time of 0.05 milliseconds. So the total paging time is about 8 milliseconds, including the hardware and software time. So remember also that we are looking at only the device service time. So if a queue, for example, of a process is waiting for the device, we have to add the queuing time as we wait for the paging device to be free to service our requests, and increasing even more the time to page in. Okay? So basically, if we try to compute, the page fault rate should be between 0, less than or equal to the probability, and less than or equal to 1. So that is going to be the page fault rate. So if P is going to be 0, then there will be no faults. But if P is going to be equal to 1, then every reference will become a fault. So basically, we have learned about this last time, the effective access time, and it is computed as the 1 minus the probability multiplied by the memory access plus the page fault overhead plus the swap page out plus the swap page in. So as an example for the demand paging, consider, for example, we have a memory access time of 200 nanoseconds, and the average page fault service time is 8 milliseconds. So to compute for the effective access time of that, using the formula 1 minus P, we can multiply it by 200 nanoseconds plus the P multiplied by 8 milliseconds. So we can get the answer 200 plus P. P is the probability multiplied by 7,999. 7,999,800. So if one access out of 1,000 causes a page fault, then the effective access time will be equal to 8.2 microsecond. So this means that there has been a slowdown of a factor of 40%. Okay? Now, if we want performance degradation to be less than 10%, we need to keep the probability of page faults at the following level. And what is that level? Like for example, in this case, 220 should be more than 200 plus 7,999,800 multiplied by the probability, which means the probability now will become less than 0.000025, which means that one page fault in every 400,000 memory access. So that's going to be a degradation of 10%. An additional aspect of demand paging is the handling and overall use of swap space. Input-output to swap space is generally faster than the file system. Now, it is faster because swap space is allocated in much larger blocks, so in larger chunks. So definitely it has less management needed than the file system. So one option for the system to gain better paging throughput is by copying an entire file image into the swap space at process startup and then performing demand paging from the swap space. So the obvious Disadvantage of this approach is the copying of the file image at the program startup. And the second option, which is the one practiced by several operating systems such as the Linux and Windows, is to demand page from the file system initially, but to write the pages to swap space as they are replaced. This approach will ensure that the only needed pages are read from the file system, but that all subsequent paging is done from swap space. Some systems, they attempt to limit the amount of swap space used through demand paging of binary executable files. So demand pages for such files are brought directly from the file system. However, when page replacement is called for, these free frames can simply be overwritten. And using this approach, the file system itself serves as the backing store. However, swap space must still be used for pages not associated with a file, and it's known as the anonymous memory. Anonymous memory means these are pages that are not associated with a file. For example, it belongs to the stack or to the heap, right? So these pages include the stack and heap for a process, and this method appears to be a good compromise and is used in several systems including Linux and BSD Linux. So typically, mobile systems do not support swapping. Instead, demand page is coming from the file system and reclaim read-only pages such as the code. Now, there is a technique known as what we call the copy on write, or the cow technique. And this allows the parent and the child processes, which are initially to share the same pages. And these shared pages are marked as copy on write pages, meaning that if either process writes to a share page, a copy of the share page is created. This is illustrated in the next image, wherein the process is being copied to have a second copy here, okay, using the same pages. So as we have denoted, if either of the process modifies a share page, only then is the page copies. So the cow allows more efficient process creation as only modified pages are copied. So in general, free pages are allocated from a pool of zero fill on demand pages, and this pool should always have free frames for fast demand page execution. So from the figure, this is the illustration wherein we can see before the process 1 modifies the page C. So you can see that this process, and this is process 1 and this is process 2, they are both accessing the physical memory, wherein there are pages in the physical memory such as the page A, page B, and page C. So on the next slide, you will see that they have modified the page C, and that page C created another copy. A copy of page C was created, and it was saved in the physical memory. Now for the page replacement, it takes the following approach. If no frame is free, we find one that is not currently being used and free it. So we can free a frame by writing its contents to swap space and changing the page table and all other tables to indicate that the page is no longer in the memory. So we can now use the freed frame to hold the page for which the process faulted, and we modify the page fault service routine to include page replacement. So what does page replacement do? They can do the following. They can prevent over allocation of memory, and it is being done by modifying page fault service routine to include page replacement. Also, the page replacement used or modify the dirty bit to reduce overhead of page transfers, which is used only to modified pages are written to the disk. Lastly, page replacement completes separation between logical memory and physical memory, wherein the large virtual memory can be provided on a smaller physical memory. So, for example, in this particular illustration, we can see that there is a need for page replacement. So, how do we know that there is a need for page replacement? The fact that there are no free frames, for example, this is depicted by this question mark symbol that you can see from here. So, it happens when there is an over allocation of memory. For example, while a process is executing, a page fault occurs, and the operating system determines where the desired page is residing. Is it in the secondary storage? But when it looks on the secondary storage and finds that there are no free frames on the free frames list, this will mean that all the memory is in use. So in this situation, there are no free frames. That means all the memory is in use, and this question mark determines that in the physical memory there will be no available space. So that is why there is a need for page replacement. And most operating systems combine swapping pages with page replacement, which is a technique that we're going to describe as we go along. Okay? So here we will see some routines or steps wherein the basic page replacement is being done, wherein the freed frame can hold the page for which the process is faulted. This is done by modifying the page fault service routine to be able to include the page replacement. The first is to find the location of the desired page on the disk, and then find a free frame. If we can find a free frame, then we use that frame. But if there is no free frame, we use a page replacement algorithm to select a victim frame. So a victim frame is used as a page replacement algorithm. Now, after that, we write the victim frame to disk if dirty. The third step is to bring the desired page into the newly free frame and then update the page and frame tables. Number 4, we continue the process by restarting the instruction that caused the trap. So we can notice that if no frames are free, 2 page transfers, one for the page out and one for the page in, are required. So this situation will probably doubles the page fault service time and definitely will increase the effective access time accordingly. So here is the illustration of the steps that we have stated a while ago. Number 1 is to find the location of the desired page, and this is done by swapping out the victim page. And number 2, we find a free frame, and this is done by using a page replacement algorithm to select a victim frame. Number 3 is to swap the desired page in, and that means to change the page in the frame table. And lastly, number 4 is to reset the page table and continue the process from where the page fault occurred. Now we must solve 2 major problems to implement the demand paging. So number 1, we must develop a frame allocation algorithm and a page replacement algorithm. So that is, if we have multiple processes in the memory, we should decide how many frames to allocate to each process, and when page replacement is required, we must select the frames that are to be replaced. Now, what is frame allocation algorithm? So it determines how many frames to give each process and which frames to replace, while the page replacement algorithm, it indicates that we want the lowest page fault rate on both first access and re-access. So evaluating the algorithm is done by running it on a particular string of memory references, wherein we call it the reference string, and we compute the number of page faults on the string. Alright? Now, we can generate reference strings artificially by using a random number generator, for example. Right? Or we can trace a given system and record the address of each memory reference. So the latter choice produces a large number of data on the order of 1 million addresses per second. So to reduce the number of data, we use two facts. First, for a given page size, and the page size is generally fixed by the hardware or system, we need to consider only the page number, right, rather than the entire address. Second, if we have reference to a page P, then any references to page P that immediately follow will never cause a page fault. Page P will be in the memory after the reference, so it will never cause a page fault. Right? So in this example, the reference string of reference page number is the following sequence of the string, no? It's from 7 to 1. So that's 701, 203, 042, 303, 032, 120, 1701. To determine the number of page faults for a particular reference string and page replacement algorithm, we also need to know the number of page frames available. And obviously, as the number of the frames available increases, the number of page faults decreases. And for the reference string considered previously, for example, we would only have this typically number of strings. Alright, so in contrast, with only one frame available, we would have replacement with every reference. So this illustration, we illustrate this several page replacement algorithm by using this particular reference string, no? This is the particular reference string that we will use for a memory with 3 frames. And the simplest page replacement algorithm is what we call the first in, first out algorithm. The first in, first out algorithm, replacement algorithm, is associated with each page the time when the page was brought into the memory. And when a page must be replaced, the oldest page is chosen. So definitely, so that's why it's called first in, first out. So we can notice that it is not strictly necessary to record the time when a page is brought in. So we can create a first in, first out queue to hold all pages in the memory. So we replace the page at the head of the queue, and when a page is brought into memory, we insert it at the tail of the queue. For example, in this reference string, our 3 frames are initially empty. So the first references 701 cause page faults and are brought into these empty frames. So the next reference 2 replaces page 7 because page 7 was brought in first. Since 0 is the next reference and 0 is already in the memory because of this, we have no fault for this reference. Alright? And the first reference to 3 results in replacement of page 0 since it is now first in the line. And because of this replacement, the next reference is 0. Okay? So the next reference to 0 will become the fault. Now page 1 is then replaced by page 0. And this process continues as shown in the figure. Okay, so as you can see, the figure was replaced. So, and so on, no? So on. So every time a fault occurs, we show which pages are in our 3 frames. And there are 15 faults altogether. Okay, in this example, as we have the following string, so we notice in the first in first out algorithm, it is done like for example, in this case we have 3 frames wherein 3 pages can be in the memory at a time per process. Since we have this reference string, then therefore the paging should be equal to the following. So in the first page 7 was placed and then followed by 0, so we have 7 and 0, and then the third number on the string is 1, so we have 7 0 1. Now the next in the line is 2, and it replaces 7 because 7 was already allocated. Okay, so as the algorithm denotes, the first to be allocated should be the first to be ousted. So therefore 7 was out and 2 replaces it, and that is why the sequence now becomes 2 0 1. Now since we already have 0 here, we cannot allocate it because we already have 0. Then therefore we proceed with the next in line, which is 3. Now there is no 3 in 2 0 1, therefore we need to replace 0 because 0 was the oldest from here because 7 was replaced already. So the next to become the oldest was 0. So in the algorithm, 0 was replaced. So the string now becomes 2 3 1. And 0 comes next, so we will have to replace 1 because 1 now becomes the oldest. So the string now becomes 2 3 0, and then it will be replaced by the next one, which is 4. So as you can see from the first one up to the end point, so the final string will now become 7 0 1. Although this is very efficient, but it is not very effective at all times. So this is one of the algorithm that we can use for the page replacement algorithm. Now let's try to consider a string of 1 2 3 4 1 2 5 1 2 3 4 5, wherein if we try to add more frames, it can cause more page faults. And in this case, the one that we have described in the graph, wherein in this graph it mentions the relationship between the number of frames versus the number of page faults, which means that if we add more frames, the number of page fault decreases. However, in this case, we will notice that even if we add more frames, it can cause more page faults. This anomaly is known as Belady's anomaly. So we can consider from the graph, for example, if we have one number of frame, we have 12 page faults. Two number of frames, we have 12 faults, which is okay. But if we add more frames, like for example like 3, we have now 9, which is okay because it's decreasing, because it should be the number of frames should decrease if we add the number of the number of page faults will decrease if we add number of frames. However, if we add more frames, like for example, we added another one, so we have 4 frames, but now the number of page fault increases. So it increases to, from 9 it becomes 10. So this fault is what we call the Belady's anomaly. So basically this happens in the first in first out algorithm wherein we encounter some anomaly. So basically first in first out is not efficient at all. It can be optimal at times, but in many cases it becomes not efficient. Because of the Belady's anomaly, another algorithm was developed, and this is what we call the optimal algorithm. This algorithm replaces the page that will not be used for a longest period of time. And that is 9 is optimal for the example. So how can we do this? Because we cannot read the future, right? So we're referring for a page that will not be used for a longest period of time. So consider in our same example, we have the same number of reference string, which is 20 pages. And we have the following example. We can see from this example, we can see in the we need to populate our page frames with the strings. Now, like for example, we have 7, then we have the next is 0, so we populate 7 and 0, and the next is 1, is becomes 7, 0, 1. Now we need to populate 2 in our frame. Now we need to choose the victim. And what is the victim? The victim is the one that we are supposed to replace with. Now how do we do that? In optimal algorithm, we replace the page that will not be used for the longest period of time. So by looking on the future, that means we have to look on the pages that will come. Okay? So we need to compare which among of these pages will not be used for a longest period of time. So definitely 0 is not our victim because 0 will becomes next. And definitely 1 is not our next victim because 1 here, over here, will be is the first before 7. Therefore, we need to replace 7 because 7 is here, right? 7 will not be used for the longest period of time. Therefore, we need to replace 7. So if we replace 2, we replace 7 by 2, so the frames now will become 2, 0, and 1. Okay? Now, the next is 0. So we cannot replace 0 because 0 is already here, right? So we disregard 0. Now, the next one is 3. So we need to look from 2, 0, 1, which one will become our next victim. And we need to look for the page that will not be used for the longest period of time. And what is that? So we need to analyze from these strings which one is not going to be used for the longest period of time. So definitely we have 203, right? Or 201. So which one will not be replaced? Definitely it's not going to be 0 because 0 is the next one, right? Next from 3. And definitely it's not 2 because 2 is going to be next after 4. So definitely it's 1 because 1 is over here. So we need to replace 1. So if we replace 1, 1 will become our victim. It's going to be replaced by the 3. Now we have the frame 203. Next is 0. We cannot replace 0 with 0. That's why we disregard this replacement. So the next is 4. Okay? So we need to find the victim, which one is next. And the victim that should be replaced is the number that is not going to be used for the longest period of time. Again, we examine the strings. So 2 will not be replaced, of course, and 3 will not be replaced because 2 and 3 are in succession. And the last is 0. So we have 2, 3, and 0. 0 is the last to be used for the longest period of time. Although we have 2, 3, and 0 here, which are going to be replaced, the longest period of time that should be replaced is 0. Therefore, we need to replace 0 by 4. So we have the string 2, 4, and 3, and so on. So this is the optimal algorithm, which is an example of stack algorithm that don't suffer from the Belady's anomaly. So definitely it goes with the relationship of the number of frames. As we added the number of frames, we decrease the number of pages or page faults. If the optimal algorithm is not feasible, perhaps an approximation of the optimal algorithm is possible. And the key distinction between the first in, first out and the OPT algorithm or the optimal algorithm, other than looking backward versus forward in time, is that the FIFO algorithm uses the time when a page was brought into the memory, whereas the OPT algorithm, it uses the time when a page is to be used. So if we use the recent past as an approximation of the near future, then we can replace the page that has not been used for the longest period of time. And this approach is what we call the least recently used, or the LRU algorithm. So basically, the algorithm goes like this. As an example, we have similar reference string. So we need to allocate 7, and then comes 0, and then the next is 1. So the algorithm states that we need to replace the page that has not been used in the most amount of time. Meaning, of course, since 7 was the first that we have used, so we need to replace 7 because we cannot replace 1 because it has been recently used. We cannot also use 0 because it is next to 1. Therefore, we can replace 7 as the victim. We can use it as the victim because it's the least recently used. So therefore, we replace 7 by 2. Now, we cannot replace 0 because 0, we cannot allocate 0 because 0 is already in the page frames. So therefore, we have 2, 0, 1 here. Now, on the next string, we have 3. So we need to look at the frame that we have, which is 201, which among these 3 should be our victim. So we cannot replace 2 because it has just been recently used, right? So the first that should be replaced here is 1. All right, so it should be 203. Okay, again, we cannot replace 0 because 0 is already allocated. So the next is 4, right? So actually the LRU is the opposite of the OPT algorithm. So again, we cannot replace 0 here because 0 is just been allocated. So from here we will see from 203 we have the next to be allocated is 4. Okay, which among these 3 should be replaced and should be chosen as the victim? We cannot replace 0 because it has just been allocated. Okay, so the list recently used is 2, therefore we need to replace 2 with 4. So the string now will become, or the frame now will become 403. Next is 2. So we cannot replace 0, we cannot replace 4, therefore 3 is going to be replaced. So now we have 402. Okay, now next is 3. Which among this 402 should be replaced? Which one is the list? The list now will become 0. Okay, because we have just replaced 4 here and replaced 2 here, right? So the list is 3, and so on. So all in all, if we try to complete the following, we will have 12 faults, which is better than the first in first out, which has 15 faults, but worse than the optimal algorithm, because in the optimal algorithm we have, I think we have only 9 page fault, no? But this one has 12 faults. So generally LRU is also a good algorithm, but they are frequently used, and LRU is another example of stock algorithm, and it does not suffer from Belady's anomaly. The LRU policy is often used as a page replacement algorithm and is considered to be good, but the major problem is how to implement the LRU algorithm or replacement. So an LRU page replacement algorithm should require, or can be required, or may require substantial hardware assistance, and the problem is to determine an order for the frames defined by the time of the last use. And two implementations are feasible, namely time counter implementation and stack implementation. In the time counter implementation, we associate with each page table entry a time of use field and add to the CPU a logical clock or counter, and the clock is incremented for every memory reference. So every page entry has a time counter variable, and every time a page is referenced through this entry, a copy of the value of the clock into the timer counter. So when the page needs to be changed, we look at the time counters to find the smallest value, and we search through a table is needed. Okay, another approach is what we call the stack implementation. So in here we keep a number of stack page numbers in a double link form, namely the page reference. Okay, so whenever a page is referenced, it is removed from the stack and put on the top. So in this way, the most recently used page is always at the top of the stack, and the least recently used page is always at the bottom, right? Another algorithm is what we call the LRU approximation algorithm, but however in this algorithm it needs a special hardware, and in this form a reference bit is used for a page which is set by the hardware whenever that page is referenced, and reference bits are associated with each entry in the page table. So initially all bits are cleared by the operating system, and as the process executes, the bit associated with each page is reference set to 1 by the hardware. So after some time we can determine which pages have been used and which have not been used by examining the reference bits, although we do not know the order to use, the order of use I mean, and this information is the basis for many page replacement algorithms that approximate LRU replacement. There is another algorithm called second chance algorithm, and the second chance replacement is a first in first out replacement algorithm plus a hardware provided reference bit. So when a page has been selected, we inspect its reference bit, and if the value is 0, alright, the value is 0, we proceed to replace this page. But if the reference bit is set to 1, we give the bits, or we give the if the reference bit is set to 1, we give the page a second chance, and then we move to the we move on to select the next first in first out page. So when a page gets the second chance, its reference bit is cleared and its arrival time is reset to the current time, right? So in addition, if a page is used often enough to keep its reference bit set, it will never be replaced. So this is what we call the second chance algorithm. So one way to implement the second chance algorithm, sometimes referred to as the clock algorithm, is through a circular queue, as you can see from the illustration. So a pointer that is a hand on the clock indicates which page is to be replaced next. So when frame is needed, the pointer advances until it finds a page with a 0 reference bit. So as it advances, it clears the reference bits. So in this figure, you can see once a victim page is found, the page is replaced and the new page is inserted in the circular queue in that position. So notice that in the worst case, when all bits are set, the pointer cycles through the whole queue, giving each page a second chance. So it clears all the reference bits, selecting the next page for replacement, and the second chance replacement degenerates the first in first out replacement if all bits are set. So we can improve the second chance algorithm by using a reference bit and modify bit if available. No? In this case, we take the ordered pair, which is the reference, and modify. Like for example, in this case, 0, 0, which is neither recently used nor modified, will be the best page to replace. And then 0, 1, which will mean not recently used but modified, which is not quite as good but must write out before the replacement. And 1, 0, recently used but clean, probably will be used again soon. And 1, 1, recently used and modified, probably will be used again soon and need to write out before replacement. So each page is in one of these 4 classes. So when page replacement is called for, we use the same scheme as in the clock algorithm, but instead of examining whether the page to which we are pointing has the reference bit set to 1, we examine the class to which the page belongs. So we replace the first page encountered in the lowest non-empty class, and we will notice that we may have to scan the circular queue several times before we find a page to be replaced. So the major difference between this algorithm and the simpler clock algorithm is that here we give reference to those pages that have been modified in order to reduce the number of input outputs required. So there are many other algorithms that can be used for page replacement. For example, we can keep a counter of the number of references that have been made to each page and develop the following 2 schemes, no? Like the least frequency use, or the LFU algorithm, which replaces the page with the smallest count, or we can have the most frequently used algorithm, which is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. So we can try, and we can expect, as might expected, neither the MFU or LFU replacement is common. So they are very uncommon to be used, and the implementation of this algorithm is expensive, and they do not approximate the optimal replacement well. Aside from the page replacement algorithm, we have a type of algorithm called page buffering algorithm. So this is another procedure wherein, for example, where systems commonly keep a full of free frames always, no? They always do this. So if they do this, the frame available when needed, no? When a page fault occurs, a victim frame is chosen, and then the desired page is read into a free frame from the pool before the victim is written out. So this procedure allows the process to restart as soon as possible without waiting for the victim page to be written out. So when the victim is later written out, its frame is added to the free frame pool. So, and an expansion of this idea is to maintain a list of modified pages. Whenever the paging device is idle, a modified page is selected and is written to secondary storage. So we modify the bit and then we reset. And this scheme increases the probability that a page will be clean when it is selected for replacement and will not need to be written out. Another modification is to keep a pool of free frame but to remember which page was in each frame. And since the frame contents are not modified when a frame is written to secondary storage, the old page can be reused directly from the free frame pool if it is needed before the frame is reused. So no input-output is needed in this case. So when a page fault occurs, we check whether the desired page is in the free frame pool. If it is not, we must select a free frame and read into the pool. In certain cases, applications accessing the data through the operating system's virtual memory perform worse than if the OS provided no buffering at all. So a typical example is the database, which provides its own memory management and input-output buffering. Applications like this understand their memory use and storage use better than does an operating system that is implementing algorithms for general purpose use. Furthermore, if the operating system is buffering input-output and the application is doing well, then twice the memory is being used for set of input-output. So in another example, data warehouses frequently perform massive sequential storage reads followed by computation and writes. So the LRU algorithm would be removing old pages and preserving new ones, while the application would more likely be reading older pages than newer ones as it starts its sequential reads again. And because of such problems, some operating systems they keep copy of the page in memory as input-output buffer, and the application keeps the page in memory for its own work. Alright? Operating system can provide direct access to the disk, getting out of the way of the applications. Now, another issue of allocation is how do we allocate the fixed amount of free memory among the many processes. So, for example, if we have 93 free frames and 2 processes, how many frames does each process get? Okay? Like for example, in this case, each process needs minimum number of frames. The IBM 370, for example, can handle 6 pages for the instruction SS move, and then this instruction is 6 byte and can actually span up to 2 pages, and the 2 pages to handle from and the 2 pages to handle to. So definitely The allocation of frames needs a maximum of cores, which is total to the frames in the system. And two major allocation schemes are needed, namely the fixed allocation and the priority allocation. However, there are many variants of allocation, as we will have to discuss here. Another important factor in the way frames are allocated to the various processes is page replacement. With multiple processes competing for frames, we can classify page replacement algorithms into two broad categories, namely global replacement and local replacement. So what is global replacement? This is the process of selecting a replacement frame from the set of all frames, and one process can take a frame from another. So the process execution time can change while this greater throughput, so more this global replacement is more commonly used. In local replacement, each process selects from only its own set of allocated frames. So we can have more consistent per process performance using this, but possibly underutilized memory, right? So this is the difference between the global versus the local allocation. In our previous example, we covered the virtual memory and we assume that all main memory is created equal, or at least that is accessed equally. What about if we have a non-uniform memory access, or we call it the NUMA, because many systems with multiple CPUs is described as NUMA, where the speed of the access to memory varies. That's why we have this type of many multiple CPUs. Okay, in these systems, a given CPU can access some sections of the main memory faster than it can access the others. And these differences are caused by how CPU and the memory are interconnected in the system. Such a system is made up of multiple CPUs. So in this example, we can see that this is the architecture. Okay, so given this architecture, we have 4 CPUs. So there are interconnections between over a system bus, but this is what we call a non-uniform memory access, where the speed of the access to the memory are varying. Because for example, if CPU 0 will try to access memory 0, it will become faster. But if CPU 0 will try to access memory 1, so there will be latency, as well as memory 3 and memory 2. So the speed of the access to the memory of every CPU varies. That's why it's called non-uniform memory access. So the optimal performance of the NUMA access comes from allocating the memory close to the CPU. So whichever memory is closer to the CPU, it will have the optimal performance. Otherwise, the least performance will be discovered. So in this particular case, this was solved by the Solaris by creating iGroups, wherein they created a structure to track the CPU and the memory low latency groups, and they use my schedule and pager. And then when possible, schedule all threads of a process and allocate all memory for the process within the iGroup. Okay, thrashing happens when, for example, if a process does not have enough frames, so it doesn't have the minimum number of frames it needs to support pages in the working set, so the process will quickly have page fault. Now, at this point, it must replace the existing page or the existing frame. Okay, however, since all its pages are in active use, it must replace a page that will be needed again right away. So it quickly faults again and again, and replacing the page that it must bring back in immediately. So this high paging activity is called thrashing. So it's the process, this process of thrashing is done if it is spending more time paging than executing. So you might expect, thrashing result in a severe performance problems. So in this illustration, you will see the problem of thrashing, where a process is busy from swapping the pages in and out. This scenario is based on the actual behavior of early paging systems. So what the OS does is to monitor the CPU utilization. This is the CPU utilization. And if the CPU utilization is too low, we try to increase the degree of multiprogramming by introducing a new process to the system. A global page replacement algorithm is used, wherein it replaces the pages without regard to the process to which they belong. Now, suppose that a process enters a new phase in its execution and needs more frames. It starts faulting and taking frames away from other processes. And these processes need those pages. However, so they also fault, taking frames from other processes. And these faulting processes must use the paging device to swap pages in and out. So as they queue up for the paging device, the ready queue empties. Okay? As the processes wait for the paging device, CPU utilization decreases. Okay? So this is what happened during the thrashing. The CPU utilization decreases. To prevent thrashing, we must provide a process with as many frames as it needs. But how do we know how many frames it needs? So one strategy starts by looking at how many frames a process is actually using, and this approach is defined as the locality model of process execution. So in locality model, it states that a process executes and it moves from locality to locality. So it migrates from one locality to another. And a locality is a set of pages that are actively used together. That's why a running program, for example, can be composed of several different localities and can have overlapping. Okay? The working set model is based on the assumption of locality, and this model uses the parameter delta, which is defined as the working set window, a fixed number of page references. So here we can see that the total number of pages referenced in the most recent delta, which stated as the something that varies in time, wherein the working set of process P, for example, is defined as if the delta is too small, it will not encompass the entire locality. But if the delta is too large, it will encompass several localities. And if the delta is infinity, then it means that it will encompass the entire program. An example is given below. So in this example, given the sequence of memory references, so if the delta is equal to 10 memory references, then the working set at time t1 is equivalent to 1, 2, 5, 6, and 7. So by time t2, the working set has changed to 3 and 4. So the accuracy of the working set depends on the selection of the delta. If the delta is too small, as I have said here, it will not encompass the entire locality. But if it is too large, it will encompass several localities. But if it is infinity, it will encompass the entire program. The most important property of the working set is the size. So if we can compute the working set size, say WSSI, for each process of the system, we can then consider that D is equal to the summation of the WSS, or the working set, where D is the total demand for frames, and each process is actively using the pages in its working set. So if the process I needs the working set frames, okay, the total demand is greater than the total number of available frames. So thrashing here will happen. Thrashing will happen if the total demand is more than the available number of frames, because some of the processes will not have enough frames. So once the delta has been selected, the use of the working set model is simple. The operating system monitors the working set of each process and allocates to that working set enough frames to provide with its working set size. So from this figure, we can see that there is a direct relationship between the working set of a process and its page fault rate, wherein the working set of a process changes over time. So that's going to be the delta, as the references to data and code sections move from one locality to another. So assuming there is sufficient memory to store the working set of a process, the process is not thrashing. The page fault rate of the process will transition between peaks and valleys over time, and this general behavior is shown in this figure, okay, where the peak in the page fault process rate occurs when we begin demand paging a new locality. However, once the working set of this new locality is in the memory, the page fault rate falls. And when the process moves to a new working set, the page fault rate rises towards a peak once again, and returning to a lower rate once the new working set is loaded into the memory. The span of time between the start of one peak to the next peak represents the transition from one working set to another. So the working set model is successful, and knowledge of the working set can be useful for pre-paging, as we have discussed, but it seems a clumsy way to control thrashing. A strategy that uses the page fault frequency, or PFF rate, which uses local replacement policy. The specific problem is how to prevent the thrashing, and thrashing was a high page fault rate. So we want to control the page fault here, the rate of the page fault, because when it is too high, we know that the process needs more frames, no? Conversely, if the page fault rate is too low, then the process may have too many frames. So we can establish upper and lower bounds on the desired page fault rate, as it was illustrated here. That means if the actual page fault rate exceeds the upper limit, we allocate the process another frame. But if the page fault rate falls below the lower limit, we remove a frame from the process. So we can directly measure and control the page fault rate to prevent thrashing. So that is the essence of the page fault frequency algorithm. The allocation of kernel memory is done using something differently from the user memory. The allocation of kernel memory is done by allocating from a free memory pool. The kernel requests memory for structures of varying size. However, some kernel memory needs to be contiguous. For example, for input-output devices. And there are two schemes of allocating kernel memory, namely body system and slab allocator. In the body system, the kernel allocates memory from fixed size segment consisting of physically contiguous pages, wherein the memory allocated is using a power of 2 allocator, which is actually satisfying request in unit size as power of 2, and then it requests rounded up to the next highest power of 2. When a smaller allocation needed that is available, current chunk split into 2 bodies of next lower power of 2, and then it will continue until appropriate sized chunk is available. So as an example of the body system, let's say we have 256 kilobyte of chunks available, but the kernel requests 21 kilobyte. So the chunk will be splitted into 2 ways, such as AL and AR of 128 kilobyte each, and then it will be further divided into 2, namely BL and BR. The 120 kilobyte will be divided into 64 kilobyte, and then it will be further divided into CL and CR with 32 kilobyte each. So definitely the one that will satisfy the request of the kernel. So the advantage of this is that it quickly coalesces unused chunks into larger chunk. However, the disadvantage is it will create fragmentation. Another strategy is what we known as the slab allocator or the slab allocation. This is the another strategy for kernel allocating kernel memory. And the term slab means it's made up of one or more physically contiguous pages, and the cache consists of one or more slabs. So there is a single cache for each unique kernel data structure. For example, it has a separate cache for the data structure representing the process descriptors, and a separate cache for file objects, a separate cache for semaphores, and so forth. And each cache filled with objects, and these objects are instantiations of the kernel data structure that the cache represents. So for example, the cache representing semaphore stores instances of semaphore objects. The cache representing process descriptors stores the instances of process descriptor objects, and so forth. So the relationship among slabs, cache, and objects is shown in our example here, no? Wherein the figure shows 2 kernel objects. So we have 3 kilobyte kernel objects and 7 kilobyte kernel object, which are stored in separate cache. Okay, so the slab allocation algorithm uses this cache to store these kernel objects, and when these cache are created, a number of objects which are initially marked as free are allocated to the cache. So they are allocated to the cache. So the number of objects in the cache depends on the size of the associated slab. So for example, a 12 kilobyte slab made of 3 contiguous 4 kilobyte pages could store 6 2 kilobyte objects. So initially, all the objects in the cache are marked as free. So when a new object for a kernel data structure is needed, the allocator can assign any free object from the cache to satisfy the request, and the object assigned from the cache is marked as used. So an obvious property of pure demand paging is the large number of page faults that occur when a process is started, and this situation results from trying to get the initial locality into memory. So pre-paging is an attempt to prevent this high level of initial paging. And the strategy here in pre-paging is to bring some or all of the pages that will be needed into memory at one time. So in the system, using the working set model, for example, we could keep with each process a list of pages in its working set. And if we must suspend the process, for example, due to the lack of free frames, we remember the working set for that process. And when the process is to be resumed, because for example, input outputs has finished or enough free frames have become available, we automatically bring back into memory its entire working set before restarting the process. So in some cases, pre-paging may offer an advantage, but the question is whether the cost of using pre-paging is less than the cost of servicing the corresponding page fault. So it may be well the case that many of the pages brought back into memory by pre-paging will not be used. So for example, we can assume that the S number of pages are pre-page and the alpha of these S pages is actually used such as 0 is less than or equal to the alpha and less than or equal to 1, which means if alpha is close to 0, then pre-paging losses, but if the alpha is close to 1, pre-paging wins. The designer of the operating system for existing machine have a choice concerning the page size. So page size is sometimes decided by the designer. However, page size selection must take into consideration the following. They take into consideration the fragmentation, page table size, resolution, input output overhead, the number of page faults, locality, TLB size, and effectiveness. However, the page size is always in the power of 2, so usually in the range of 2 raised to 12 or 4096 bytes up to 2 raised to 22 or 4,194,304 bytes. On the average, the page size is growing over time. So we have mentioned before, especially in chapter 9, the last topic that we have, that the TLB reach is the amount of memory accessible from the TLB. So TLB is the transaction look around buffer or lookout buffer. So the meaning is the definition is that the TLB size is multiplied by its page size to get the TLB reach. So ideally, the working set of each process is stored in the TLB. Otherwise, there is a high degree of page faults. So if you try to increase the page size, this may lead to an increase in fragmentation because not all applications require a large page size. If you provide multiple page sizes, this will allow the applications that require larger page sizes the opportunity to use them without an increase in fragmentation. For the examples of the operating system, Windows uses demand paging with clustering. It allows pages surrounding the faulting page. Windows also uses processes that are assigned working set minimum and working set maximum. The working set minimum is the minimum number of pages the process is guaranteed to have in the memory, and the process may be assigned as many pages up to its working set maximum. It happens when the amount of free memory in the system falls below a threshold, automatic working set trimming is performed to restore the amount of free memory. And the working set trimming removes pages from the processes that have pages in excess of their working set minimum. For the Solaris, it maintains a list of free pages to assign faulting processes. So we have the following terms. They have the lots free, wherein the threshold parameter or the amount of free memory to begin paging is used. And then they have the des free, the threshold parameter to increasing paging, and the min free, the threshold parameter to being swapping. So paging is performed by page out process, and page out scans pages using modified clock algorithm. So definitely Solaris has more implementation of the page replacement algorithm. So scan rate is the rate which pages are scanned, and this ranges from slow scan to fast scan. Page out is called more frequently depending upon the amount of free memory available. Solaris also uses priority paging, which gives priority to process code pages. So finally, we take a look at this program structure, wherein we can see that demand paging is designed to be transparent to the user program, and in many cases the user is completely unaware of the page nature of the memory, and in other cases system performance can be improved if the user or compiler has an awareness of the underlying demand paging. So we take a look at this one, this program structure. This is a C language program, and let us assume that pages are 128 words in size. So we consider this C program whose function is to initialize to 0 each element of this array, 128 by 128 array. And the following code is typical, and that we notice that the array is stored row major. The array is stored data 00, right? And for pages of 128 words, so we will notice that each row takes one page, and the preceding code zeros one word in each page. So definitely this code zeros all the words on one page before starting the next page. So it reduces the number of page fault to 128. So if we examine carefully the data structure and programming structure, it can increase the locality and hence lower the page fault rate and the number of pages in the working set. So from this topic, we have learned that virtual memory abstracts the physical memory into extremely large uniform array of storage, and the benefits of virtual memory is that a program can be larger than the physical memory. A program does not need to be entirely in the memory, and the processes can share memory. Processes can also be created more efficiently. We have discussed a lot of techniques. One of the techniques is the demand paging, where pages are loaded only when they are demanded during the program execution. Another topic that we discuss is about page fault, and it happens when a page is currently not in the memory where it is accessed. So the page must be brought back from the backing store into available page frame in the memory. We discussed the copy on write, which allows a child process to share the same address space and its parent. Okay, and then we discussed the page replacement algorithm, which includes the first in first out, the optimal, and the least recent used algorithms. We also discussed global page replacement algorithms and local page replacement algorithm. Thrashing occurs when a system spends more time paging than executing. And finally, we discuss about kernel memory, where the kernel memory is allocated differently from the common user mode processes. In kernel memory allocation, memory is allocated in contiguous chunks of varying sizes. And the two ways to allocate memory are the body system and the slab allocation. So that's it for our chapter. Thank you.